So this video is meant to cover a whole bunch of ground and show you a whole bunch of things about what can happen if various things occur. I want to show you how to deal with something called compute star local consistency radius. And so the premise of this example is that you're going to drive from Nova Scotia down to Miami, Florida. You shouldn't be doing this by car, but let's say you are. Maybe you have a big van and you're taking a group of friends and you're going to drive the entire way, never sleeping, because you're just going to switch drivers and sleep on the way. Bad idea. Really bad idea? Well, let's do it anyway. So Google claims that it's about 32 hours, but in my model, I'm allowing about 44 hours. So anyway, the idea as you go from city to city, you may choose different options. Like you may choose to go around through a different city, and that's going to change your projected arrival time. Okay, so that's the theory behind the model. As it turned out, linking all the cities together that I wanted to link, it ended up being too big, which was an important learning objective. So I had to actually break the problem into smaller units. But this is a picture of unit 1 and 2 together, I believe. I'm calling these places where I break them, I call them pinch points. So for example, over here, Providence is a pinch point. All right, so Providence, everybody has to go through Providence, so it's a good place to break the model into two pieces. And I'll explain a little bit more about why that's so important computationally when I get to the explanation of what is actually going on inside the code, okay? But for now, just at a high level, just understand that it's much better to break it into pieces and then glue it back together. And I'm going to show you how I did that. Okay, so here is the code that I put all the information in here about the location, the geometry goes in here so that I don't have to mess with the geometry. But I have adjacency lists 1, 2, 3, 4. And then adjacency list 1, 2 is just 1 and 2 combined together. And adjacency list 2, 3 is just 2 and 3 combined together. So that we can do a little bit of exploration with that. Now, my initial starting values down here are my solutions that I just came about by hand. I just did them on paper with some exception. This one here was optimized by the computer, Providence that is, and Philly, and Tallahassee. I grabbed those from the computer as I was computing them for the reason that I want to be able to glue them together at the join points, and if I'm not allowing the computer to optimize that initial location, I wanted all the pieces to glue together nicely. So other than those pinch points, everything else is going to be optimized by the computer, but I started out myself putting these values in, okay? All right, so far so good, hopefully. Let me go back to this map and give you an example of why this is a problem. So I started out pretty simple, going from Nova Scotia to Bangor and so forth. And the problem occurs when you start having multiple paths to the same place. And let's say if I'm going to go to New Haven, Connecticut from Hartford, I could go straight to New Haven, or I could go through New London. So if they don't add up, right? One would be less than an hour and one would be more than an hour, and they're both sort of competing. And so I'm actually kind of abusing the technology because the code assumes path independence, and I've just violated path independence, and I want to see what the computer does to me when I violate path independence. Okay, but before I get into that fully, I want to just show you how to turn on these different pieces. My default is going to be that list 1 is going to be active, but the start node is going to be whatever the first item of the list is. So I'm not going to look at this anymore. This is just the geometry telling me the suggested distances between cities, and the units are hours. These are units of hours. All of them are units of hours. Down here, it's hours from Nova Scotia. All right. Nova Scotia is not in the United States. All the other cities are in the United States. Nova Scotia is in Canada. Okay. So what I'm going to do is down here, I'm going to see which list I want to use. And let me start with list 1. And then I'm going to just run this code and show you that the resulting suggested hours, the supposed suggested hours is, I forgot, where am I going? To Providence maybe? No, I'm not going to Providence. Hold on a second. I got to figure out what my city is. Yeah, it's Providence. I'm ending on Providence because this is the first link. So I'm suggesting that it takes about 8.7 hours to get to Providence from Nova Scotia. And, okay, let's just make a note of that. I'm going to go back to Google and just sort of paste it in here. Save that number for myself for later. Okay? And so now I'm going to run this, I'm going to run the second adjacency list, which starts there. And again, I hard-coded the starting value so that it would match. So it should match. We said it was about 8.7, and that value should be the value that I wrote in. So I hard-coded this, so this has to start here. This is frozen. Everything else is being optimized. And so where I'm ending up is Philly down here. Okay, so I'm going to copy this. All right, so this is when I split the problem into 2 pieces. Here are my ending values. Okay, now I want to know what happens instead if I glue these 2 pieces together. So I'm going to use adjacency list 1, 2. Now this is going to relax the condition in the middle. Let's see if we still get the same distance in the middle, the same time distance. So recall, we want to make sure that this is consistent, that I'm going to get 8.7 in Providence and 6.25 in Philly. And what do I get in, where's Providence? These are all scrambled. Yep, there it is. And Philly, yes, it's the same. So in this case, the condition on Providence was relaxed, and we still ended up getting the same values. So whether I join the first 2 pieces or calculate them separately, I'm getting the same answers, and you can verify that. So that's kind of a fun thing to do. And it makes intuitive sense, because if everybody has to pass through that city, then you should be able to separate the problem into those pieces. Okay, and again, we'll talk about why computationally it's important to do that, because otherwise you're not going to have enough time to solve the problem. The computer is just going to run forever, and it's going to bore you, and you're going to get frustrated. So if you have a pinch point where you can break the problem up, you really should. Okay, one thing I wanted to show you is that since we are violating this condition of path independence, we have to manually do that extension, and I did that in the code over here. All right, so if you see when I run the code, first I tell you the bogus consistency radius, and that is a false advertising. This process that is being used, what we did is we only maximally extended the start node, and that's okay. If you actually have path independence, then that step is enough. And we've been doing that in the past, and I wanted to show you it's no longer valid, because now, since we're violating path independence, we actually have to maximally extend all the nodes, and then after we fully extend everything, we get a reasonable consistency radius. Because otherwise what's going to happen, the reason I wanted to point out the good one and the bad one like that, is you may see your bogus consistency radius and think, oh, how come the code is giving me something worse than what I started with? Well, it didn't. Actually, what actually happened is this is your bogus consistency radius that would have been, that process would have been fine if we'd had path independence. We don't. So if you manually extend everything, you get the correct value for your initial consistency radius. And when you compare the 42 and the 35, you actually did optimize. And why was it so good to start with? Because I did it by hand, and it wasn't really off by that much. But if I had just started with all zeros or something, then this number would have been horrible. But it's fairly good only because I did the puzzle by hand and estimated, right? So these values these values are all the times to travel from Nova Scotia to these various cities. Okay, and it's a reasonably accurate result based on the information I gave the computer. The other thing you're going to notice is local star consistency radius, and I'm going to talk about that in just a second. Okay, so I apologize. The green numbers that were up here were from a different model. I've now updated them to reflect the model we're actually using. So what you want to know about this local consistency radius per node is it tells you everything downstream from that node. So for example, I am asking for the entire sheaf. What is its consistency radius? Well, it's about 36 and 35.7. Okay, and it should be the same as the star local consistency radius at the top because of the way I've drawn this. Like everything, this is a post set that has a single entrance point and a single ending point. So there's some special things going on here that make the problem easier. Okay, but in this case, I just want you to see like that works. And so you should think of this as the sum of the squares of the errors. And we'll get into that in just a second, but it should grow as you go upstream. So the entire consistency radius for the whole sheaf should be equal to the local consistency radius for Nova Scotia because everything downstream in the sheaf is downstream from Nova Scotia. So for example, this isn't true for any other node. It's only true for Nova Scotia. And the other thing you should know is that if there's one final ending point or several ending points, their consistency radius has to be 0 because there's nothing downstream from it. And notice New York City isn't bad. It's just 0.06. There's only one path downstream from New York City. It goes from New York to Philly. So there's not much opportunity to introduce error because there's only that one little step, and it so happens that the 14.5 plus 1.7 is close to 16.2. Again, excuse me, some of these numbers are not perfect. I think I should have put 14.6 on New York. But anyway, these are very close, and I simplified this for the purpose of discussion, so the numbers aren't 100% accurate. You can see the actual numbers come out in the code, and you can play with them to your heart's content. But this is just for the purpose of explaining. Okay, I think now is a good time to give this little example of how we get the consistency radius on Scranton so that we can explain, so we can understand how the whole thing fits together and understand why it's so important to split this problem at the pinch points. Again, I'm sorry, I just updated these red numbers because it was the other red numbers are slightly off because we were using a different model, but I want this demonstration to be fairly accurate, so I want you to understand where these numbers are coming from. Okay, let's start with the path from Scranton to New York City that goes directly. So the red number, 14.032, is the data on that node that says, so far as we've been optimizing, we think that the distance from Nova Scotia to Scranton is 14.032 hours. And then I'm going to add the blue number, which is the number that I coded in saying how much time I think it should take to go from Scranton to Philly. And then that's going to be 16.032. And I'm going to subtract out 16.194 to give me an error. Okay, I'm going to go ahead and do that. So I get an error of negative 0.162, and I square it to get 0.0262. All right, and I'm going to do similarly with the other pathways. Okay, and from there downstream, everything seems to work. Okay, so the takeaways from this arithmetic is just the fact that there's 4 paths going from Scranton to Philly, because when I say all the paths going from Scranton to Philly, I mean it doesn't have to either start or end on Philly. It just means of all the possible paths within this region that start from Scranton and go downstream, like New York to Philly is in that set of paths that can happen. Okay, so I just wanted to make it clear which paths are being calculated, and if that makes sense, it should make sense now why it is both ridiculous not to split at the pinch points, and also why it shouldn't make any difference, right? Because all those extra combinations are just getting multiplied in over and over and over, and you're just making the computer go through a whole bunch of repetition that it doesn't need to go through. It's not going to improve your results at all. It's just going to get in the way and waste a lot of time. So that is just to explain what's going on, how these things are being computed, and why you don't want to make the computer do that. Okay, so hopefully this was helpful to you. It was fun for me to do. I hope you enjoyed it too.